Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel, and today's topic of discussion is air-piloted valves. Our objective is to examine air-piloted directional control valves in pneumatic systems. This lecture operates under the presumption the viewers watch the Pneumatic Directional Control Valves lecture, available at the Big Bad Tech channel. If you haven't watched this lecture yet or only dimly recall its contents, please take the time to do so now and return to this lecture when you are so qualified. You recall, in the aforementioned lecture, we discussed manual, mechanical, and electrically actuated pneumatic directional control valves in some level of detail, but I admittedly kind of left you hanging with respect to air-piloted valves. Well, today I intend to rectify that impasse and talk your ears off about air-piloted valves. Viewers that have slogged through the hell of the hydraulics playlist might recall that I kind of just wave my hands and passingly refer to oil-based hydraulically piloted valves, but I never really go into any detail about them. For good reason. At risk of setting the internet on fire, I will so boldly proclaim that oil-based pilot systems absolutely disgust me, and I hate working on them. And this is coming from a guy that loves hydraulics. Don't get me wrong here. Hydraulics are the systems of choice for certain applications, and for those specific applications, I get super excited. And when I say excited, I mean really excited, like heart beating harder and my respiration increases type of excitement. But to make hydraulics do something it doesn't do well, when there are so many other better choices, I get super pissed off and I start headbutting walls, doors, and people. Hydraulics does one thing well, and no other system does it better. Seriously, none. Moving a tremendous load is not an extraordinary feat, and any number of different types of systems can do that. Lifting the load and then locking it in place and just staying there, that's the challenge. This is what hydraulics do well, principally because of liquid's incompressible nature. To accentuate my point about this, I'm asking the viewer to keep this lecture playing, get out of your chair, get off your couch or whatever, and stand on one leg and extend the other leg straight out. And then stand there, and stand there, and stand there. Stand like a statue. If you're not a wimp, grab a 50-pound slam ball and hold it over your head and stand there, and stand there, and stand there. Get my point? The best type of system to move a load and lock it in place is a hydraulic one, principally because of liquid's incompressible nature. But to suggest that hydraulics is the best choice for any and all applications is seriously flawed. Hydraulics excels at brute lifting or crushing strength. To suggest that this same raw power also be used for control is akin to using a 3.5-inch 12-gauge shell filled with 2 ounces of number 4 lead shot to kill a hummingbird. Even if one was capable of overlooking the obvious overkill, hydraulic systems are undoubtedly dirty, messy, greasy, oily, heavy, and present contamination, slip, and fire hazards. The last thing you want in a hydraulic system is more hydraulics. Again, this is coming from a guy that loves hydraulics. For this reason, if any desire of precise control is desired in a system that must also exert the strength of a silverback, my immediate choice would not be an entirely hydraulic nor an entirely electrical system, but rather an electrically controlled hydraulic system. Hydraulics provides the necessary brute strength, whereas the electrical ladder logic and solenoid-actuated directional control valves provides the timely, efficient, and precise control of such strength. It is the best of both worlds. Strength without the sloppiness and speed without weakness. This being said, those technicians that service electrically controlled hydraulic systems must necessarily be conversant in both languages, hydraulics and electrical control. Given the topic of this lecture is air-piloted valves, it might seem like this rant about hydraulics and electrically controlled systems is somewhat divergent, but I'm hoping to tie it together with this astute observation. This mismatch between primary and pilot, or power control, does not exist in pneumatic systems, and one may encounter pneumatic systems entirely controlled by air pilots without the necessity or expense of electrical control. In summary, the medium to light-duty nature of pneumatics is a perfect match for both primary power and pilot control. Additionally, air-piloted directional control valves offer distinct advantages in pneumatic systems. Allow me to demonstrate. Consider a normally closed, push-button operated 3x2 directional control valve used to control a spring-retracted, pneumatically extended single-acting cylinder. Let's say for safety reason, the operator station needs to be some distance from the actuator. In the deactivated state, the cap end is exhausted to atmosphere, and the cylinder is retracted by the spring in the rod end. When an operator presses the push button, the valve moves into a position such that pressurized flow is routed to the cap end. Given the long length of line between the pneumatic source directional control valve and actuator, one might expect significant pressure losses in the line, such that the single-acting cylinder extends weakly and slowly, if at all. Here's an example of this flawed system. I'm simulating the separation distance between the source and actuator with a huge coil of hose. When I press the push button, the cylinder does extend, but it does so with the eagerness of an 8-year-old shaking off a sugar rush the day after Halloween. For this reason, rather than directly controlling the single-acting cylinder, one might consider relocating the source closer to the actuator and indirectly controlling it using an air-piloted, normally closed 3x2 directional control valve. Instead of a manual actuator, this valve makes use of an air pilot to shift the spool. At the operator station, still some distance from the actuator as required for safety concerns, another push-button operated, normally closed 3x2 directional control valve, instead of opening and closing the primary passage, and directly actuates the air-piloted directional control valve closer to the actuator. You note the large separation distance still implies the dash pilot line will experience pressure losses and consequent reduction of flow rate, but who cares? It's a pilot line. It only needs the tiniest, weakest puff of air to shift the tiny spool. In the deactivated state, the cap end is exhausted to atmosphere and the cylinder is retracted by the spring in the rod. When an operator presses the push button, a pilot signal is sent to the air pilot on the left-hand side. The air-piloted valve moves into a position such that pressurized flow is routed to the cap end. Given the close proximity of the relocated pneumatic source, the system does not experience any significant pressure losses in the line, such that the single-acting cylinder extends with the requisite strength and speed. Here's an example of the reconfigured system. Again, the huge coil of hose simulates the separation distance between the push-button operated valve and the air-piloted valve. This being said, the source is now much closer to the actuator. When I press the push button, it sends a tiny, tiny puff of air to the air-piloted directional control valve, which is all it needs to shift the spool such that the cylinder extends with the necessary strength and speed. In summary, air-piloted valves don't need a lot of pressure nor flow to move a tiny spool. All they need is the tiniest puff of air to change position. Pilot systems are exactly that. Low pressure, low flow rate control signals used to direct the high pressure, high flow rate primary system. As a means of reinforcing this point, consider a double-acting cylinder, directly controlled by two normally closed push-button operated 3x2 directional control valves, both some distance from the actuator. When an operator presses push button 1 on the left, the cylinder does extend, but extends slowly and weakly due to the pressure losses in the line feeding the cap end. To compound this poor performance, the line exhausting the rod end encounters a lot of resistance such that the cylinder is doubly slow and doubly weak. The same poor performance is experienced during retraction. When an operator releases push button 1 and presses push button 2 on the right, the cylinder does retract, but it retracts slowly and weakly due to the pressure losses in the long line feeding the rod end. To compound this poor performance, the line exhausting the cap end encounters a lot of resistance such that the cylinder retracts doubly slow and doubly weak. One means of correcting this flaw is with the use of a double air-piloted 5x3 directional control valve indirectly controlled by two normally closed push-button operated 3x2 directional control valves, still the requisite distance from the actuator. When an operator presses push button 1 on the left, it sends a tiny puff of air to the air pilot on the left-hand side, shifting the air-piloted valve into a position such that pressurized input 1 is routed to actuator port 4 and actuator port 2 is vented to exhaust port 3. Given negligible losses in the short primary lines, the cylinder extends with undiminished strength and speed. The same can be said for retraction. When an operator releases push button 1 and presses push button 2 on the right-hand side, it sends a tiny puff of air to the air pilot on the right-hand side, shifting the valve into a position such that the pressurized input port 1 is routed to actuator port 2 and actuator port 4 is vented to exhaust port 5. As with extension, given negligible losses in the short primary lines, the cylinder retracts with undiminished strength and speed. Other important features of indirectly controlled air-piloted valves can be examined in this application, notably memory and priority. Let's examine memory first. You note the double air-piloted 5x3 directional control valve does not have an offset spring nor a preferred deactivated state. The two air pilots work in opposition to one another. When the air pilot on the left is asserted, the valve shifts to a position that extends the cylinder. When an operator stops pressing push button on the left, the spool remains in this position and the cylinder remains extended. Whereas, when the air pilot on the right is asserted, the valve shifts to a position that retracts the cylinder. When an operator stops pressing push button 2 on the right, the spool remains in this position and the cylinder remains in retraction. This begs the question, what happens when you turn the system off? In the absence of any new pilot signal, the system simply remains in the last asserted state because of memory. You'll again note the double air piloted valve does not have an offset spring because the two air pilots work in opposition to one another. This means when a particular air pilot is asserted, it shifts the spool into that position and the spool just stays there, even if that particular air pilot signal is lost. The only way to move the valve into the opposite state is to assert the other pilot. Memory is a desirable feature for several reasons, the principal one being safety. For example, if an operator pressed and released push button 1 to extend the cylinder to lift some heavy load, and then cut both pilot lines and tossed them on the floor to writhe around like a pair of snakes with their heads cut off, the cylinder would remain extended and the load remain lifted because the double air piloted valve remembers the last asserted state. Another feature of air piloted valves can be demonstrated with this application, that of priority. As I stated earlier, the only way to shift this double air piloted valve to the opposite position is to assert the opposite air pilot. This isn't entirely true, because it neglects to mention that one must also exhaust the original air pilot to allow it to shift. As previously, consider the act of extending the pneumatic cylinder. When an operator presses push button 1 on the left, the air pilot shifts the valve into a position such that the cylinder extends. Rather than releasing the push button 1 as previously, the operator instead keeps mashing it down and the air pilot on the left-hand side remains pressurized. Along comes operator 2 and mashes down push button 2 on the right-hand side. It too sends an air pilot signal to the valve. However, because the air pilot on the left-hand side remains pressurized, the spool doesn't shift and the cylinder remains extended. After all, operator 1 got there first, and operator 1's first action has priority over late arriving operator 2. Only when operator 1 releases push button 1 would it exhaust the air pilot on the left-hand side. Now, an operator can press push button 2 and send a valid air signal to the air pilot on the right. The air pilot shifts the valve into a position such that the cylinder retracts. Again, rather than releasing push button 2 as previously, operator 2 instead keeps mashing it down and the air pilot on the right-hand side remains pressurized. Along comes operator 1. He's like, damn it, I told that cylinder to extend. And angrily mashes down push button 1 on the left-hand side, which again sends an air pilot signal to the valve. However, because the air pilot on the right-hand side remains pressurized, the spool doesn't shift and the cylinder remains retracted. After all, taking advantage of operator 1's absence, operator 2 is now assumed priority. Only when operator 2 releases push button 2 could operator 1 extend the cylinder. Neat, eh? Priority ensures systems resolve conflicting inputs in a predictable fashion. All right, now that we've explored some of the advantages and applications and discussed memory and priority exhibited by air pilot valves, let's take a look at a simple pneumatically controlled or air-piloted pneumatic system. And recall the previous double push-button operated system necessitated the press of one button to extend the cylinder and another to retract it. This seems a little wasteful of an operator's time. Would it be nice to have an operator extend a cylinder at the press of a single button and then have it automatically retract at the limits of extension? One way of implementing this function is by using a double-acting cylinder controlled by a double air-piloted 5x3 directional control valve, indirectly controlled by two normally closed 3x2 directional control valves. One push-button operated as previously, and this time, the other one mechanically operated with a roller. At the limits of extension, the roller is positioned such that the rod strikes the roller, thus shifting the directional control valve on the right-hand side. When our operator presses push button 1 on the left, the air pilot shifts the valve into a position such that the cylinder extends. While extending, the operator releases push button 1, and the air piloted valve remains in this position and the cylinder continues extending. At the limits of extension, the rod strikes the roller and shifts the roller-operated valve on the right-hand side to a position that allows pressurized input to reach the air pilot on the right-hand side. At the limits of extension, the rod strikes the roller and shifts the roller-operated valve. This allows pressurized input to reach the air pilot on the right-hand side. Necessitating no input from the operator, the air pilot shifts the valve into a position such that the cylinder retracts. During the act of retraction, the rod stops striking the roller, and the spring offset returns the roller valve to the deactivated closed state, thus exhausting the air pilot on the right-hand side and resetting the system for another single-cycle reciprocation. Here's a real-world example of this system. When our operator presses the push button, the air piloted valve shifts and the cylinder extends. Upon striking the roller, it sends another air pilot to the opposite side, shifting the valve back, and the cylinder retracts automatically. All right, let's explore a couple scenarios using this air-piloted system, keeping in mind memory and priority exhibited by air-piloted valves. Scenario 1. An operator presses and releases push button 1. As previously, the air pilot on the left-hand side shifts the valve into a position such that the cylinder extends. While extending and before striking the roller valve, the whole plant suddenly goes dark. Pressure in the pneumatic source drops to 0, and all airflow stops, primary and pilot. What happens? Given there's no pressure, nor airflow, most likely the cylinder comes to stop midway between extension and retraction. While the system is in the dark, an operator actually gets up out of their chair and goes over to inspect the system, placing their eye immediately below the tip of the rod. You, the technician being asked to troubleshoot the sudden failure of the pneumatic source, quickly resolve the issue. But before you turn it back on, what are you going to say to the operator looking at the rod? And why are you going to say it? Here's what you're going to say. Put some safety glasses on, buddy, because this air-piloted valve has memory and maintains the last asserted state. Given air pressure was lost while extending, the spool of the air-piloted valve remains in the position allowing extension. Upon restoration of air, the cylinder continues extending, pressing the back of the operator's head against the roller valve, thus retracting the cylinder. Scenario 2. Priority. Sometimes you don't want extension followed by immediate retraction. Sometimes you want to extend and hold it for a bit before you retract. To allow this functionality, my advice would be to press and hold push button 1. Why is this true? This is true because the air-piloted valve is exhibiting priority. When an operator presses push button 1 and holds it down, the air pilot on the left-hand side remains pressurized. Even if the roller is struck and sends a pilot signal to the air pilot on the right-hand side, the double air-piloted valve remains in this position allowing extension because the air pilot on the left-hand side was pressurized first, thus it receives priority, effectively ignoring the roller valve input. Only when an operator releases push button 1 will the air pilot on the left-hand side be exhausted, allowing air pilot on the right-hand side to shift the spool to a position allowing a retraction. Scenario 3. Troubleshooting. Now, there is no limit to the crazy stuff that can and does happen in an industrial setting, but consider what happens if the roller actuator is a little sticky, either because of age or uncleanliness, and when actuated, remains triggered. What happens and why? Will the system work as intended, and for how long? This is also a priority scenario. Most likely, you'd observe the following. When an operator presses push button 1 on the left, the air pilot shifts the valve into a position such that the cylinder extends. At the limits of extension, the rod strikes the roller and shifts the roller-operated valve into a position that it sends a signal to the air pilot on the right-hand side, which shifts the air-piloted valve into a position such that the cylinder retracts. During the act of retraction, the rod stops striking the roller. However, the sticky roller remains triggered, and the roller valve remains in a position that continuously sends a signal to the air pilot on the right-hand side, thus not resetting the system for another single-cycle reciprocation. Outwardly, nothing is amiss because the system did perform a single-cycle reciprocation as intended. However, when an operator attempts to repeat this action, it won't work. Why? Priority. That's why. With the air pilot on the right-hand side remaining pressurized by the inadvertently actuated roller valve, the double air-piloted valve remains in the retraction position because the air pilot on the right has priority over any new input. Only when a technician frees and cleans the sticky roller or replaces it with a new one will the system stop asserting retraction as priority and reliably perform single-cycle reciprocation as intended. All right, hopefully this quick discussion and demonstration of air-piloted directional control valves got you thinking. We'll explore more applications of air-piloted valves after we discuss two important logic valves, the AND or dual pressure valve and the OR or shuttle valve in later lectures. In conclusion, this lecture examined air-piloted pneumatic directional control valves. We discussed the advantages of air-piloted valves and explored several air-piloted applications. Additionally, we introduced the concept of memory and priority exhibited by air-piloted pneumatic directional control valves. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.